Hello, everyone, and welcome to another episode of the GC 100 podcast. I'm your instructor and host, Dr. VG. All right, today we're going to really connect the dots, so to speak. We're going to examine atmospheric pressure and then apply our understanding of atmospheric pressure to local and global circulation patterns. So let's get going. So the overview will examine pressure, and then as promised, we're really going to kind of tie it to airflow properties, to global circulation patterns, as well as local circulation patterns. So what is atmospheric pressure? It is produced by the weight or the mass of a column above a unit area. And so, as we've previously thought about, air weighs something, and the more air column above you, like literally the more mass there is. And so that produces pressure. It's weighing down on us. And so air pressure is the measured weight of that air column. And so as you go up in elevation, there's less and less air weighing down on you. So there's less and less pressure. And so we have air pressure decreasing with increasing altitude. This curve represents this known relationship with decreasing pressure with increasing altitude. Although it is variable over space and time, we can kind of estimate rather generally, approximately that decrease related to that air column. So how high is the troposphere or our total atmosphere, and how much mass then is weighing down on us? Okay, so let's examine some additional properties of our atmosphere and density here. So, is cold air more or less dense than warm air? So this isn't, it kind of sounds like that. Is there more or less moisture? But let's just think about density, which is really like how many molecules per unit volume. What do you think? Is cold air more or less dense than warm air? Well, if you thought cold air was more dense, then you're correct. If not, no worries. Let's examine why. And so one thing I like to kind of like focus on, or that I appreciate, is that when we're cold or molecules are cold, they don't move much. And so literally when conditions or atmosphere are cold, we have lots of molecules packed closely together, meaning we have more mass per unit volume. When air temperatures warm up, the energy, remember kinetic energy, temperature is is a measurement of essentially motion. And so as molecules warm up, they get faster, they bounce off of one another and they create more space. And so there's literally less mass per unit volume. And so then simply cold air is more dense than warm air, and warm air is less dense than cold air. And so effectively, this has higher air pressure because there's more mass. And so remember, our measurement of pressure is effectively the measurement of mass, the weight above you. So cold air is higher pressure, has higher pressure. It's more dense, and then warm air has effectively lower air pressure. How do we measure air pressure? We measure it with a barometer, and there's a variety of units of measurement. We could measure the atmospheric pressure in inches of mercury. And so we think about this measurement of inches of mercury, which is like literally the atmospheric column weighs down. Imagine you had this like pot of mercury, which probably isn't a good idea, but effectively you're measuring that pressure that rises in the tube as a result of that pressure. And so the same thing happens to water. Air is weighing down on water. And if you then within a column allowed it to equilibrate, you can measure that height of water as a displacement. So they're not the same because mercury is a denser fluid, but they're both being affected. Ultimately, for us, just appreciate we can measure pressure, and there's places on Earth that have higher pressure and places on Earth that have lower pressure. And then even over time, we here in Marquette or wherever you might be will experience large, higher pressures systems come in and they move away, and a lower pressure system comes in. So we'll explore that in more detail starting now. And so we can measure pressure and effectively then when there's lower pressure, as in the left diagram, the key take-homes is a low pressure system is a circulating body of air. And so literally it's moving in a circular fashion. And in this way, we have air at the surface, and this is the key part. At the surface, our air is converging toward that low pressure center. And then when they meet, then air rises or ascends. And so you have converging and rising or converging and ascending under a low pressure center. And so it looks something like that. Whereas under a high pressure center, you have air descending. And so literally air up high is descending, coming down to the surface of the earth. And when it hits the earth, it has to go somewhere. And so imagine you have a big pile of sawdust and you have like a vac or a hose or like an uh, some kind of air you blow down in the air and then the sawdust goes everywhere outwards. And so here you have air descending and diverging at the surface. And so that is a key where your air is sinking, right, falling to the surface and then diverging. Both have this circular pattern, but here we're converging and here we're diverging. So we'll explore this in more detail moving forward, but these are two of our major atmospheric pressure systems, and they largely influence wind speeds and even temperatures on Earth. So let's explore that in a little greater detail. And so ultimately, on very uh, small scale, so large geographic extents here, we can think about differential heating. And so where Earth is being heated more vigorously, there creates warmer and colder air. And so just by doing that, you have this air mass or air masses across the surface of the Earth that are trying to flow like literally horizontally to equilibrate. And so in general, like not necessarily like a measured surface wind speed, but in general, this air mass is trying to move to the low air mass from high to low pressure to equilibrate. And so that is this process of advection, which creates wind. And so we'll explore more what happens to wind as it interacts with Earth's surface and various other factors. But ultimately, via advection, air masses move from high pressure to low pressure, generally speaking, across a continental scale. So that is important to like appreciate that this is a continental scale perspective. This air mass is generally moving from west to east. However, when we measure, like literally observe wind direction and wind speed at the surface of the earth, that is going to then more relate going backwards to these processes where we have surface air converging or surface air diverging. So this is this next figure. We're going to use and reuse this figure and a couple others within this lecture, but also within some applied exercises and other activities. And so here I really like this simple graphic depicting a high pressure center or system and a low pressure system. So again, remember in this graphic, we have air descending divergent. It's coming straight down to my laser pointer here. And then when it hits the ground, it has to go out and away. And so literally the air is going to go out and away in every direction. And as that kind of example, like imagine having this big pile of sawdust and you have like an air compressor or something, and you're just pushing air straight down to the surface. All of that then from the center is going to go out and away, and you're going to push all your sawdust out and away. Whereas the opposite then, with a low pressure center, you have air converging at the surface and then ascending. And so above my laser pointer, the air is literally like coming up directly towards us in this. And so they're both circular systems. And then we can think about whether they have clockwise or counterclockwise motion. Winds are like the direction of wind. When we look at a weather forecast and they say strong north-northwest winds or strong northwest winds, it means the wind is coming from the northwest. And so whenever you hear and when we use the term wind direction, make sure to always apply it where it is coming from. And so this kind of shows this graphic for wind direction. To repeat this, and you're going to see it a couple times because these are kind of really major concepts that we can apply at local, regional, as well as global scales. And so under a high pressure center, you have air descending and diverging, and under a low pressure center, you have air converging at the surface and then ascending or rising at that low pressure surface going vertically upward. So now let's connect some of our understanding of atmospheric pressure and think about how it's interacting with our surface. And so one of our four major types of uplift as a review, and we'll come back to these uplift processes here and in future lectures. But just simply appreciate that convective uplift is the uneven heating of Earth's surface. It produces convective air currents. And so somewhere on Earth's surface is being heated vigorously. Hot air does it want to rise or fall? It wants to rise. And then as air rises, we've also learned about adiabatic processes. It starts cooling as that air expands, and then it equilibrates, and finally it cools enough where it then just falls back down. And so that is a convective cycle or a convective current. And so simply, and as I just kind of described, air near Earth's surface heats up, it rises, and then it cools and it sinks. And so there's our convective loop. Another process, so this is affecting wind. So all what this second section is really just kind of understanding what processes influence wind advection and convection here. And so what is causing wind to occur? And so this is one process causing wind to occur. This could happen on a local scale, like near Marquette versus Negaunee or out on Lake Superior. And as we'll learn later, it also most definitely happens on a global scale, tying back some of our previous content focused on the subsolar point as a hint for the future. Another major process that we just kind of covered in another graphic to think about this, wherever there are high pressure systems and low pressure systems, and this could be on kind of a regional to continental scale, thinking Iowa, Illinois, Ohio, Michigan, and beyond. And so here, we have this high pressure system, and here's a low pressure system. And generally speaking, this air mass is trying to move this way. Another aspect that's really important with understanding wind speeds as well as directions is this concept of a steeper or larger gradient, where anytime you have a large gradient, meaning a big change over a unit space compared to somewhere else where there's not as much change in pressure over a unit space. So again, this is an isobar map showing 1020 millibars of pressure down to 1010, down to 1000. And so over the space, you have the most change on this map, where here you're really only changing by perhaps 5 or less, and here you're changing 10 or more millibars. Anywhere there's a great or larger gradient, you expect larger wind speeds. And so that's a big take home. And then the converse is true, where there are smaller pressure gradients, so less pressure change over space, you expect lower gradients. And so on this map, here's a location. These arrows, literally the same distance here on our screen or on the slides, showing the larger gradient, and you expect higher wind speeds, and you would expect lower wind speeds. So we'll come back and practice that in a few different ways moving forward. So now we're going to add some complexity, but mostly just to appreciate that air doesn't just move from the equator to the pole, and it doesn't just kind of keep that same distance. And as we can appreciate in thinking about like wind speed, and wind direction on even a local or continental scale, it's affected by so many different things. It's affected by different air masses coming together, and it's most definitely here affected by our surface. And so as air masses move across a continent, they're occurring and interacting with the surface, which causes friction and then turbulence and frictional flow. And so frictional force is strongest right here at the surface, and they will create these kind of convective eddies or cycles. And so mostly what I just want to appreciate is that even though your air mass could be moving from like the Western US to the Eastern US, wind direction at any given place, it could actually, like in this case, it could be opposite just because of these frictional deflection and reflection forces, so frictional forces. And so just appreciate that wind speeds are affected by many conditions, including friction, as well as on a larger scale as this Coriolis effect. And so what is the Coriolis effect? So now on a continental scale, we can appreciate this deflection of air masses. And so as an air mass perhaps generates in the Atlantic and it comes up the eastern seaboard of the US through Florida and the Carolinas, literally it's being deflected because the Earth is rotating underneath it. And so these air masses can often take days or even weeks to migrate across the continental or global scale, and at which time the Earth is revolving underneath it, and it creates this apparent deflection known as the Coriolis effect. And so what this looks like ultimately, literally, as you would track it in the northern hemisphere, air masses have this apparent deflection to the right, and then under in the southern hemisphere, air masses have this apparent deflection to the left. And this then here is what is known as the Coriolis effect. And it literally, if you were to track an air mass here coming from the north to the south, you would literally observe that air mass to have this apparent deflection. That is another way in which air masses are affected by our Earth system. So there's some animations we can check out to better appreciate the Coriolis effect. I have a more serious question for you, though. This is definitely going to be on a quiz or an exam. Just kidding. But let's check it out anyways. Does the water in your toilet bowl swirl counterclockwise? Swirl clockwise in the northern hemisphere and counterclockwise in the southern hemisphere because of this Coriolis effect? Is that what causes our toilet bowls to swirl in different directions in different hemispheres? Well, the answer is no. It's all about the mechanics of the toilet, but could be cool. Moving back on to more serious topics. Anyway, so airflow integration at the surface. So I realize that I'm adding elements, Coriolis effect and frictional forces, and it's not meant to confuse you. Mostly, and for this class especially, I just want us to appreciate that these forces are working on air masses, and as we appreciate air circulation, we just have to take into consideration, or at least appreciate that there are both like local, regional, and global scale influences on air systems. But I do want to come back to low pressure and high pressure because this is so very important in terms of understanding air movement and air circulation across the Earth. And as we'll see here in the next couple sections, at global scales as well as local scales. And so understanding high and low pressure systems. So let's come back to this kind of integrating our understanding. And so under a high pressure system, you have air descending from up high down to the surface. It hits the surface and it has to go somewhere. So then it diverges and goes out and away in all directions. The essentially kind of reverse is true then for low pressure centers. You have this warming air in the middle. That warm air is rising and it's pulling the air in. So imagine like a vacuum cleaner, literally like a shop vac, and you're holding that shop vac up above the surface, and then it's pulling all the air in at the surface and it's going up into your vacuum or into your shop vac. Literally, that's the same essentially process that's happening on Earth's surface, where all of the surface air needs to make up that air that's now rising. And so effectively, you have air converging at Earth's surface and then ascending and rising at the low pressure center. So one more time to keep practicing those concepts of high and low pressure systems. And so we come back to this map, and now, like literally based upon the location of the high pressure center and the low pressure center, you can have a pretty good gauge or estimate as to the wind direction just relative to that high pressure center. So, for example, like that wouldn't be, or it could be perfectly straight, and some of this deflection is due to all of these interconnected processes. And I don't expect us to get to that level to understand how all of convectional, frictional, and Coriolis are affecting wind speeds and wind directions and migrations of weather systems. But I do want to just simplify or at least like focus our attention here on high pressure and low pressure centers, understanding that if you are north of a high pressure center, the wind would be coming from the south, moving to the north, and it would be effectively moving in this pattern these arrows are showing. So the similar if you were at below, like literally, like if there's a high pressure center north of us up in Ontario, and we were directly, or over Lake Superior, and we were directly south of that high pressure center, we would expect air, literally, like wind to be coming from the north. And so again, wind directions are from where they originate. And so now you can just literally place yourself in any location around a high pressure center or a low pressure center to appreciate where wind is coming from, literally the wind direction. And so again, we have converging and ascending air under that low pressure center. So now let's apply our understanding to global circulation patterns and really kind of re-emphasizing these high and low pressure systems and how they work. There is definitely unequal heating of the Earth, as we've learned. And so there's much more heating near the equator due to that subsolar point and the fact the sun is directly overhead and you have that intense radiation over the equator. And so if the Earth wasn't tilted and we weren't rotating and revolving, we'd probably have a pretty simple convective loop where the poles are cold, the equator is warm, it rises, it gets drawn all the way to the poles, and then it comes back down. However, it's not quite that simple, and we'll think why. And so, because the Earth is rotating and because we're tilted and revolving, now we previously learned that migration of the subsolar point. And so, when the northern hemisphere is pointed toward the sun, that subsolar point is located furthest north, and then the equator, the subsolar point passes over the equator at both spring and fall equinoxes. And then for our northern hemisphere winter, we're effectively pointed away. And so due to these kind of connected systems now, they create what I would say are like latitudinal belts. And so on these next slides, what we're going to examine is kind of a more of an equatorial subtropical system, a mid-latitude system, and a pole system. We're really going to separate them into three major systems and think about how these convective loops are influencing the subtropics, the mid-latitudes, and the poles. So let's begin. And so the differential heating of Earth's surface then is largely creating these very large convective systems that then is driving wind speed and wind direction on the surface. And so let's reveal some of this surface wind. And so these patterns, and we're really going to start our investigation here with what is known as the Hadley cell, and then think about how the Hadley cell is affecting wind speed and wind direction near the surface. And so the separation of the Hadley cell from mid latitude to polar has really everything to do with the fact that we are tilted and rotating, and then that differential heating mechanism is effectively kind of migrating north and south, which we'll come back to shortly within this lecture. So now let's begin our journey of global circulation and focus on Hadley cells. And so what is a Hadley cell? I think it's pretty cool. And so it forms over the equator because the equator, or at least this region, is being heated more vigorously by the sun than further north or further south. Wherever Earth's surface is being heated more vigorously, you expect there to be warmer air, which is less dense, which wants to rise and will rise, and you are literally creating a low pressure system or a low pressure center. And so to kind of reframe this animation one time, so now air is gonna ascend, and then it's gonna diverge. When it ascends, it's getting, remember, expanding, it's getting a little cooler and cooler, and it equilibrates at some point, and it's then gonna get drawn poleward, And in this case, literally that air that it was ascending is going to get drawn to the North Pole and drawn to the South Pole as it descends and or ascends and then diverges up high. And so again, not to confuse terminology, here on this map, we have surface wind direction. So we have literally like air converging to this center. Air is then rising, and when it gets up high, it's then going to get pulled toward the pole. And so now we'll kind of like focus on the northern cell and appreciate that there is a southern cell. And so air rises over the equator and is drawn poleward both to the north and to the south as it equilibrates and cools down. So now showing this kind of convergence to focus on that low pressure. And so literally like over the equator, and we'll come back to this term ITCZ, which is the Intertropical Convergence Zone. Anywhere you are on this red line, that literally is very close or almost or exactly where the subsolar point is. It's the place on Earth's surface that's being heated most vigorously by the sun, and you have this low pressure system really existing all around the Earth on this global scale understanding. And so now it's creating our trade winds, literally. And so these winds that we as humans have been using for millennia now and like relying upon their direction and speeds and also some to some extent understanding their variability. But here just appreciating you have air converging at the surface and it's converging to this ITCZ to our low pressure system. And then above this line, literally everywhere you have air rising. And so you have this incredible convective uplift that's circumnavigating the Earth that's around, at least in this graphic, the equator. But then remember that that subsolar point migrates north and south. And so here, the on Earth's surface, we have what is called the Intertropical Convergence Zone, which is really the line that is closely and almost nearly perfectly resembling of where that subsolar point is. And so as that subsolar point migrates north, so does this whole entire ITCZ and the Hadley cell, which we'll appreciate here in the next few slides. We just appreciate that this Hadley cell will migrate, the whole cell will shift north as this ITCZ shifts north for our northern hemisphere summer, and then it comes back down, it crosses the equator in the fall, and then as on our winter again, then our ITCZ is migrating even further south. And so here above this ITCZ, literally everywhere, you have this tremendous amount of convective uplift and you have convergence of surface air. So the surface air is converging to that low pressure system. And really, when you're right then above where you're at that ITZZ, in terms of trade wind terminology, they call it the doldrums, because right there at that place, there is not much wind to be had or experienced, so to speak, but you would have to be north or south for those winds to pick up at the surface. So now let's we were really just focusing on this like low pressure. It was rising. And so we have converging air. It's rising and then it's getting drawn poleward. And now like appreciate that we're moving 30 degrees north or 30 degrees south in latitude and how far that is on Earth's surface. That's a huge system. This Hadley cell is massive. And so now we at some point that air gets drawn towards both poles and then it starts descending and then it descends and it hits Earth's surface and it diverges at Earth's surface. And this is a very large high pressure system. And so literally on a global scale, it's called the subtropical high pressure system. And so because you have this massive amount of air always ascending here above the ITCZ, and then it's being drawn poleward, and eventually it needs and wants, so to speak, to sink. It's all sinking nearly at the same place, and then it hits Earth's surface, it descends, and then Earth's surface, it diverges at Earth's surface. And so you have this diverging air system at the subtropical high pressure. One thing to appreciate, so now what happens? We have air rising, and when it rises, it cools, and then let's tie it to cold air can hold more moisture or less moisture. Cold air holds less moisture than warm air, and so wherever you have convective uplift, you have clouds forming and likely lots of precipitation, a very humid environment. Then the reverse here, we have that air now descending, and as it's descending, it's becoming more and more pressurized, and it's heating up literally. As you add more pressure, those molecules are moving more, and it actually becomes then warm air holds less moisture than cold air. And so you have these like clear, warm, hot, sunny skies persisting because warm air can hold so much more moisture than cold air. And you're effectively creating and like funneling in. It's just like warming up as it's coming down. And so literally the most dry places, the arid places on Earth, like Saharan Africa, occur right at 30 degrees plus or minus latitude, and then other major deserts of the world, like Central Australia, for example, then also occurring under these subtropical high pressure systems because you have this persistence of warm, sunny conditions and dry. All right. So now we're going to move northward. And we're going to come back to one graphic. I want you to appreciate that there is a mid-latitude system. However, it is much more complex and more suited, in my opinion, to like a weather and climate class and upper level class. Ultimately, that mid-latitude air mass system is really just being affected. It's kind of being bullied or pushed around by the Hadley cell from the south, and then our polar cell here from the north. And so for the class and for our understanding and then quizzes and exams, we're really going to focus on the Hadley cell and then the polar cell, and then here the polar front, which is the line that demarks the boundary between our polar cell and the more temperate mid-latitude system to the south. And so our polar jet stream, which we've covered a little bit now, here is this really concentrated band of high winds aloft, up high in Earth's atmosphere, and they literally mark the boundary of this polar cell from the mid-latitude, and they keep cold air in this cell and relatively warmer air to the south. There's often a fairly moderate or even tremendous pressure difference, creating these high wind speeds. So the undulations of the polar jet stream. So this is just half of, like, we're only looking at half of the Earth, right? In this picture, this cell goes all the way around Earth. And at some points, it can be almost perfectly circular, going all the way around Earth. And at other points, it's like you whipped a rope and it kind of has these undulations. And small undulations are normal. However, when there's very large undulations, when you're thinking like 20 degrees latitude undulations, then these really large dips or undulations in the polar front are known as Rossby wave. And this can really dramatically affect weather from one week to the next, or even one day to the next, where for us in the mid latitudes, like we're at 46.5 degrees north here, anytime we're north of the polar jet stream, it's really cold or colder anyways, depending on the season. So summer, it's colder if we're here, or winter, it's still colder. But then these Rossby waves, this kind of like moves and undulates, and then we'll literally effectively go in and out of that polar cell as this moves and undulates around the Earth. We have some animations to support that with other lecture topics. So appreciate that there are dramatic like weather environmental differences, whether you're inside north of this jet stream and cell or south. And for us in the mid latitudes, it's often when we're being affected by these Rossby waves that are then dipping down underneath us, and then they move out across to the east in the Atlantic and move on, and we kind of just wait more or less for another big Rossby wave to set up. So some basics about the polar cell. And so here we have this polar system. And so appreciate, or just at least for you, understand that there is the Hadley cell, which we covered and focused on. There is a Farrell cell, which is really interesting, but I think we're just gonna understand here in GC100 that there is a Farrell cell. I will not quiz or examine you on anything to do with the Farrell cell, but you should just understand that it's there and that if you took a weather and climate class, you would learn more about it. But here, I do want to understand or at least appreciate a little bit about the polar cell because it does really influence our weather and our climate here in Marquette. And so that line that demarks the mid-latitude Farrell cell from the polar cell here is this polar jet stream. So that would be located here in this image. And then similar, or at least kind of similar conceptually to the Hadley cell, there's air that's being drawn up high. And in this case, it's also being drawn to the North Pole. And so you have this air mass essentially rising here, and then it's going to descend and fall back down to Earth over the pole. And so you kind of have this like persistent descending high pressure system over the pole. And so even though the North Pole receives snow and precipitation, and we think that's wet, actually the North Pole and the South Pole, for the same reason, are incredibly arid. They're essentially like cold deserts. They really don't receive that much precipitation, and they are really affected fairly consistently under this descending high pressure system, which effectively typically keeps things drier, right? Because that air is warming up as it's descending, but then it's going to pass over Earth's surface that's pretty cold with very little insulation and get colder and colder and colder as it returns then here back to the south. And so here's our polar cell system from, somewhere in the mid latitudes where we are, or perhaps further north. It's going to ascend and descend and then come back down to Earth's surface. And that's really, for us, going to set up lake effect snow. All right, so let's explore the ITCZ in a little greater detail. And so again, Earth is not perfectly perpendicular to the sun. We're tilted and then we're revolving. And so there's a point at time where the northern hemisphere is tilted away from the sun, and the subsolar point here located directly above the Tropic of Capricorn. And then we revolve 180 days. And then now our Tropic of Cancer is located at the subsolar point that's being heated most vigorously. And then effectively that's just migrating from winter solstice to summer solstice and then back. And it just keeps going up and down on Earth's surface. And that is then affecting all of these cells that we just talked about. Like that Hadley cell is going to move north with the ITCZ migrating, and then it's going to move back down south. And appreciate that the Hadley cell potentially is occupying like 30 degrees latitude. That's an incredible air mass system that is just migrating with this subsolar point. So I have several links here. Really, these two links are the same video. Here's directly to YouTube, and then this is the source that shows this animation that is really great. And it appreciates that anytime you have this intense convective heating at Earth's surface, you have air rising. And when it rises, it cools, and cold air can hold less moisture than warm air, and you create clouds and precipitation. And so from a satellite view, literally, you can track this band of precipitation and clouds, and it literally like just kind of moves north and then it moves back down south for our winter, and then it just kind of keeps coming back up and down just like that. So I do recommend checking out this animation as well as this very short graphic animation from UCAR here from Colorado. I was trying to download it, but I was not able to, so it is embedded directly into this website. Go ahead and check out both of these animations and how the ITCZ influences monsoons. And so there, if you have not heard of a monsoon, appreciate that some places on Earth, and I'm just going to kind of focus on the Indian continent, subcontinent region here. And so for large portions of the year, the ITCZ is further south. And so whenever that occurs, then India is literally out of the clouds because that ITC is way further south. As it moves further south, that cloud band moves south, and then effectively India is close or under the Hadley cell when it's descending with high pressure. And so India and really any region across the globe in that same latitudinal belt had these really dramatic seasonal precipitation patterns where they go from almost extreme desert drought to incredible amounts of precipitation, just complete deluges, really. And that is a normal annual cycle, and that is what a monsoon is. And so these Asian monsoons, or just monsoons in general, is that migrating of the ITCZ. And when you're under the ITCZ, you experience tremendous amounts of rain because of all that convective uplift. And then as it migrates away from you, then, and you're being affected by that subtropical high pressure system, it is sunny, warm, and dry. So now let's kind of apply and reapply what we're learning to more local scale circulation patterns. And so this happens in Marquette, it happens near oceans, really any large landmass that's adjoining a body of water. We have both sea and the next land breezes. And so a breeze blows from the sea where there's effectively a high pressure to the land where there's a lower pressure. And so to kind of appreciate that with arrows here, what happens during the day, and we learned about this in a previous lecture topic, the land is getting heated up. And so that radiation is warming the Earth's surface much more vigorously than over the water. And when that happens, you have air rising, and convective uplift. Then, because air is rising, you have this localized, and so this is not like a Hadley scale perspective. This is very local. This could even just be out into Lake Superior to Marquette and Negaunee and Ishpeming and about that scale for your reference. And so now the land is getting heated more vigorously. You have this localized low pressure system drawing air up, it's rising, and air at the surface is going to converge and then ascend, right? And so it's going to draw this air from the water, from the sea to the land. And so this happens on the ocean, where the term comes from, sea breeze, but it also most definitely happens in Marquette. And actually, if you spend some time here in the summer, which if you haven't, I hope you can, because McCarty Beach and all of our beaches are really quite incredible. This happens very regularly on a daily basis, especially on like a calmer day. It's really nice and sunny. You're out at the beach at like noon or 1 o'clock, and it's like, oh, this beautiful day. And then all of a sudden, like 2 or 3 p.m., which remember is typically the hottest part of the day, we have the biggest convective uplift happening up like by Menards and beyond into Negaunee. And literally, like you can feel this happen on most days in the summer, at least most sunny days. It creates this like not quite instantaneous, but almost you'll feel this breeze and it just comes at you. And this is then this setup. And so we here in Marquette also feel the sea breeze. It happens, especially on a sunny day, nearly on a daily basis. So the reverse happens then at night, where the land cools down much more quickly and that water has been slowly heating up. And actually, the water and the air immediately above the water is now warmer when compared to the air above the land. So now you've like swapped. And so your local low pressure center is over the water, air is rising over the water, and then air comes back down and flows from land to the water. And so really on a diurnal cycle near an ocean or here in Lake Superior, especially in the summer and a sunny day or string of summer, sunny, warm days, you have this alternating sea breeze and then land breeze at night. The same like physical drivers then happen across the earth for the same reasons. Anywhere you have really intense heating, like the top of a ridge, for example, you have a local low pressure center, and air is going to want to rise to or converge. In this case, it's going to want to rise here for because it's in a valley. But air is always going to want to like make up that air that's rising, right? It's converging at the surface. And so here, oops, wrong way. You have vigorous heating of the ridges, and then the air down in the valley will literally rise up the valley walls to make up the fact that that air is rising to like replace that air. And for that reason, you have these like consistent valley breezes as well as mountain breezes, which are effectively the opposite at night. Then the ridges cool down and the cold air wants to sink. And so you have this like diurnal shift of wind patterns in the mountains. And this is actually a big reason why it's so hard to fight fires and contain and manage wildfires out west, because even if like the regional system isn't calling for winds, there's always winds in the mountains. And if it was a little windy, it's likely even windier in the mountains due to these valley convective heating up convection at the ridge tops and then vice versa, cooling and falling. So valley and mountain breezes. A cool phenomenon that happens in more Arctic polar climates are these katabatic winds. They sound pretty punishing. And so this is when extremely cold, dense air flows downslope because cold air wants to sink. It's dense. And so if you give it a topographic gradient, a steep gradient, like happens in Antarctica, which is a continent and has topography and even mountains. And so you have these incredibly cold, dense cold air flowing rapidly downslope at great speeds. And so these are these unique phenomenon in these like Arctic polar regions called katabatic winds. Another really cool kind of local regional weather or rather wind system is called Chinook winds. I think these are pretty neat, and it still continues to reinforce our understanding of high and low pressure systems. And so this occurs when there is a low pressure system on the leeward side, like literally now think about like a regional or continental scale, like on either side of the Rocky Mountains. For example, there's a low pressure system to the east and a high pressure system to the west. So the air is moving from the west to the east. And when you have these really strong, like it's a very low pressure system and a very high or dense high pressure system, you literally just effectively speed up this conveyor belt. Like not kind of sort of, you do by a lot. And so because of the fact that air masses want to move from high to low pressure, you're effectively like funneling much more orographic and then adiabatic rising. And so on the windward side, you're creating this recipe for lots of precipitation because of this enhanced lee or windward movement. But then on the other side, which is where the Chinook wind term comes from, you have an incredible amount of air now descending, and then it's descending, it's warming up, it's drying, and so you have very strong, warm, dry breezes on the leeward side, which is Chinook winds. So we can check out this YouTube video to highlight how Chinook winds affect largely the Intermountain West region of the US. So now let's turn our attention to the oceans and continue our journey to appreciate air and now ocean currents that are being influenced by air patterns. So ocean surface currents are driven by winds. And so going back to those like the Hadley cell and then thinking about subtropical high pressure systems, but now what happens on a global scale or subglobal scale in terms of the oceans is we create these gyres, which are circular, very large movements of water. So thinking like across continental scales here, where because you have air pushing, but then if it hits a continent like here, it needs to it deflects and then gets sent over to the west, where it gets deflected again by South America, and then it gets deflected again by North America, and you create these really kind of definitive gyres. And so we have a North Atlantic gyre and a South Atlantic gyre, and all over the world, at least in these large and really kind of subdividing the Atlantic into North and South, and then the Pacific into North and South, we have these large gyres, which are really interesting. One kind of cool fact, and so this is a heat map, if you will, temperature map, and this is Florida going up through Georgia and the Carolinas. And to kind of go back to this and think about, so now we have all this tropical equatorial water being heated up, it's being deflected, it's moving up the coast of Florida, and it all kind of originated and heated up in this equatorial region over kind of a long period of time, and then it gets deflected, and now literally that incredible amount of like stored energy is going to get sent all the way across to Europe. And so we have this kind of consistent plume of warm water that gets sent back to the Northeast. And one thing I always like to appreciate is like here is Europe, and that then related like latitudinally, you're thinking like northern portions of Canada. However, climates across Europe are much more temperate and more, kind of our Midwest or southern US regions, despite the fact that they're higher in latitude. And that has a lot and really almost everything to do with the fact that they're receiving this North Atlantic current of this kind of consistent warm water getting sent toward them. And so to explore some of these ocean currents in greater detail and to appreciate gyres, we can unfortunately also appreciate how much stuff we have humans have added to our oceans and think about what they call the Great Atlantic and then the Great Pacific garbage patches. And so the Pacific being even more pronounced, and so this happens for many reasons with pollution and just junk, but also incredible natural disasters. And so let's appreciate that there was a huge tsunami in Japan in 2011, and that was incredibly devastating. It also, as that tsunami wave came on shore and did an incredible amount of destruction, that tsunami water retreated under incredible power and force, and it literally placed an incredible amount of debris, human waste in this case, just cars, vehicles, buildings, everything out into the ocean, and where it then gets caught in this North Pacific gyre. And so our currents send junk all the way across, and really all of Canada and the Western US have received all this material that came from Japan and other places probably too, but this big pulse. But however, some of that kind of got trapped in the middle of the gyre, and it literally kind of just like migrates this way and comes back, and it kind of just stays in the middle. And they've been tracking it for a long time, and it's kind of getting smaller, but still to this day there is this like really large garbage patch, and it's not just from this one singular tsunami event. However, that was this incredible like singular amount of material added, but this is really, it just accumulates there naturally over all of the time, and all the stuff that ends up in the ocean gets trapped in this North Pacific garbage patch. Continuing our exploration of winds and then into the ocean, there are not just kind of surface winds. So we were mostly focusing on like surface wind patterns and then surface ocean current patterns. However, these processes also affect vertical mixing. And really, this is the extent of oceanography in this class, but appreciate that they're, because of these wind patterns and then how they hit continents and then the bathymetry of our underwater environment, there are these definitive areas with these downwelling currents bringing water that's typically nutrient depleted because everything's been using it down into the ocean. And then conversely, there's these areas around the world that have consistent upwelling. And often these areas are some of the most biodiverse and incredibly abundant life-wise regions because there's so many nutrients and minerals down in the ocean that aren't being used, and they get funneled upward. And so you have this like flourishing pulse of from bottom up in terms of like trophic food webs, which we'll talk about later this semester. But just think we're feeding all of Earth's ocean biota. And so these are these like incredible biodiversity hotspots around the world where you have these kind of consistent upwelling environments. All right, so now we're going to kind of wrap things up, and we're going to think about something that you've probably heard about. And so maybe you've heard about El Nino and maybe also its then counterpart, La Nina. And so what does this mean? We hear a lot about it in the news, but let's just kind of think a little more simply, if you will, about what El Nino and La Nina is. Ultimately, every 3 to 8 years, just think every few years or so, there often is this reversal of normal at the equatorial region, meaning surface ocean temperatures near the equator in the Atlantic are either colder than average or warmer than average. And so when we have what's called an El Nino event, you have this persistent belt or band of ocean water that is multiple degrees warmer than average, and then you have the reverse. And so there are some years where it's just kind of average, but often our Pacific Ocean is like oscillating or alternating between either El Nino, warmer, or La Nina, colder conditions. And this is normal and has been normal for many, many decades, hundreds, thousands of years, and even beyond. And in fact, we can even like tease some of these patterns out on a more paleo scale, if you will, looking at ice core records. I digress a little bit, but this process or this oscillation between El Nino and La Nina has been happening for a really long time. It's a natural phenomenon. It is a natural phenomenon that has major implications. And so that's what I really like to appreciate, that when there are El Nino events or when the Pacific Ocean is warmer than normal, this then has these dramatic influences on air masses moving on a continental scales. And then specifically here, and just to kind of simplify these two diagrams, when there are El Nino events, we typically expect our polar jet stream to be further east and further north, which then means our air masses from the south are more dominating the continental US. And so you have this warmer air that's then moving in from west to east, but largely more from the south under El Nino. And then the reverse, typically under La Nina, there is this more pronounced jet stream further to the south. And so now, like looking at us here in Michigan, we have this jet stream down to the south, which means we have cold air from the Arctic moving down across the continent and then flowing over Lake Superior and producing lake effect snow. And so I'm always really happy when meteorology forecasters predict we're going to have a La Nina winter because that typically means good powder skiing. With that, Dr. VG is signing off.